I would like to invite Professor Harald Fritzsch to give his talk on the composite weak bosons. Now.
Yeah, this is a very speculative lecture on composite weak bosons. Please switch down the light. Yeah, and many years ago people thought the Rho mesons are elementary gauge bosons. They turned out to be bound states, and I assume something similar for the weak bosons. And it's related to the results from the LHC. Here you know the machine of the LHC. I like this picture because here you see the Monte Bianco, the Mont Blanc, the biggest mountain in the Alps. And here is Geneva with the airport. Now at the LHC, we collide right now protons against protons with an energy of 4 TeV, the highest so far. And it was observed a new kind of bosons, which some people say it might be the Higgs boson, but we still don't know really what it is, with a mass of 125, 126 GeV. Now, I will discuss the possibility that it's not a Higgs boson, but it's an excitation of the weak bosons, and it has spin 0. Very similar to what happens in QCD. That would require, however, that the weak bosons are really composite objects. And as you well know, in the standard model we assume that the weak bosons, together with the leptons and quarks, are completely elementary. I mean completely point-like, they don't have any structure. The present limit coming from SLAC and from particularly from LEP and Tevatron is just above 10 to minus 17 centimeter. That is only valid for the electron, a little bit also for the muon, and for the up and down quarks. The other quarks we still don't know. Now in the standard model we understand well the mass of the proton. And the question is, what is the mass of the weak boson? Does it come about in a similar way, or is it something completely different? Now in the standard model, standard model means here QCD, the proton mass is just given by the field energy of the gluons and of the quarks inside the proton. And the more specific QCD calculations give, roughly speaking, about 70% of the mass of the nucleon is given by the gluons, and 30% by the field energy of the quarks. And in addition, we have also contributions from the quark masses, which are small and which I neglect for the time being. And that gives the energy, and if you divide it by c squared, you get the mass of the proton. Now the mass of the weak boson, how does it come? And just like also the mass of the electron. Well, some people say it might be related to the spontaneous symmetry breaking, which was first figured out by Faye Anderson, more in solid state physics, by Proudhon, Angler, Goralnik, Hagen and Kibbe, and by Peter Higgs. And it's usually called the Higgs mechanism because Higgs has such a short name. And but it is really the mechanism of spontaneous symmetry breaking, which is completely different from the mechanism of QCD, generating the nucleon mass. So in the Higgs mechanism, the weak bosons are generated just by the vacuum expectation value of the Higgs field, which is jumping out of the vacuum, making an interaction with the weak boson and disappears in the vacuum. And this vacuum expectation value can be calculated in the standard model because it gives the mass of the weak boson, and this we know. And so it comes out to be around 294 GeV. You might discuss another possibility, namely that the weak boson mass is also generated by a confinement mechanism, like in QCD. I prefer this possibility because, you know, the mass of a particle in physics is something universal, and it's related to gravity through general relativity. And so there should be a unique mechanism to generate masses, not two or three different mechanisms. And the way it looks now in the standard model is we have the QCD mechanism for the nucleon, the Higgs mechanism for the weak bosons and the charged leptons and the quarks, and then maybe a third mechanism generating the Majorana masses for the neutrino. Something very funny. Now, this confinement mechanism implies that the weak bosons would have to be composite. And let me compare these two possibilities by making an analogy with the Rho meson and the Higgs mechanism. Sakurai, already around 1960-61, suggested that the Rho mesons are elementary gauge bosons, and Yang and Mills were also using this possibility for the strong interactions. And in 1964, then, Sakurai could, if he didn't do it because he was not interested in that mechanism, but in principle he could have introduced the mass of the Rho meson by the Higgs mechanism. All what you need is two scalar doubles like we have in the standard model, which you have a certain mass m, and then you have the Rho mesons to be massless. And then what happens is that three of these four scalars here move over to be the longitudinal component of the Rho mesons, which get a mass of 750 MeV. And then there is a Higgs scalar with a certain mass which you don't know. And the universality of the Rho mesons, we know the Rho mesons couple universally to all the hadrons, comes in such a theory simply through the gauge invariance. The universal coupling of the Rho meson to the pions, or universal coupling to the Rho meson to the nucleon, or universal coupling to the Rho with itself, which can also be measured indirectly. It's all around 2.5 here. And that is related to the non-abelian gauge invariance. And in other words, we have the typical gauge diagrams which you have here. This is proportional to the coupling constant G, like this one, and that's proportional to G squared. But we know now that this is not correct. The Rho mesons are actually not elementary gauge bosons. They behave in a certain way as they would be, but they are indeed not. They are just anti-quark bound states. And the Higgs mechanism is also certainly not true for the Rho meson. The Rho meson mass is simply a QCD mass like the nucleon mass. So in QCD, the Rho meson is quark-antiquark with many gluons inside, and the gluons give mostly the mass of the Rho meson. The mass of the Rho is around 760, and it can be calculated in QCD as a certain constant which you can calculate. It has been calculated in lattice QCD, times the lambda C parameter of QCD, which is measured to be of the order of 250 MeV with large errors. And in QCD, of course, then you have the three massive Rho mesons, and there is no Higgs scalar at all. Of course, besides the Rho meson, there is also an omega meson in QCD. This is very understood in the quark model. Now, the universality of the Rho, how do you understand this? Well, again, you just have this duality diagram where the quark lines go through. They never end, they never are graded, they just go through. And so you get the same universality relations as we have in case of gauge invariance. And this is related to the duality diagrams given by current algebra and vector meson dominance. That was shown by Gell-Mann and also by Sakurai a long time ago. So the universality of the couplings has a different origin as in the case if the Rho mesons are gauge bosons. Again, also you have the current algebra, in particular vector meson dominance. The rho meson is dominated by the current. And again, you have these nice continuous diagrams. So if the weak bosons now are composite, they would be consisting of something smaller. Of course, this would not be quarks, something else. And there are some old references about this. The first paper suggesting such a possibility was written by Bjorkane already in 1977. I worked on this in 1981, also together in a similar way, Barbieri, Mohapatra, and also my student Dieter List, and I together with Xavier Carl-May again. And I came back now to these models in connection to the LHC result. And I wrote some new papers, which the archive numbers are here. You can easily find it by going to the archive under my name. Now let me make an analogy again of the weak bosons with the rho mesons. In QCD, we have the three massive rho mesons, well understood. But I should also point out there is another mechanism which most people don't know about, namely a dynamic mixing between the rho zero meson and the photon. And that was too fast, yeah. So a rho zero goes to a photon, and the photon goes back to the rho zero, and so on. That means a mixing between the two. And this mixing is well understood. It is a dynamic mechanism. Just comes from the annihilation of quark and antiquark into a photon here. And the mixing parameter, which is relevant, which describes this mixing, is just given by the decay constant of the rho meson divided by the mass of the rho times the electric charge. And the decay constant of the rho meson is just given by the transition matrix element between the vacuum and the rho zero of the isospin current, the isospin vector current. Now we know from experiment that F rho is around 220 MeV with large errors. So roughly speaking, the decay constant of the rho and the lambda c parameter of QCD seem to be roughly the same. That could be an accident, but I will assume that this is the case. And then I can calculate this mixing with the rho zero, and that's what you obtain. The mass of the rho zero is slightly lifted up compared to the mass of the rho plus by a factor 1 minus m squared, and m is this mixing parameter, which I defined before, given by the ratio of the decay constant divided by the mass of the rho. And you can easily calculate that mass shift is 3.1 MeV. The mixing parameter m, which is relevant here, is just is close to 0.09. So you have in QCD now this possibility that you have the charged rho meson and the rho zero is lifted up. In real nature, actually, things are more complicated. There's also a direct Coulomb in the contribution to the mass, to the rho plus and rho minus. The things are more complicated. But it's this I neglect for the time being and just consider this mixing mechanism. So it's 3.1 MeV. In real nature, we see for the W bosons, the weak bosons, a similar phenomenon. The Z boson is lifted up by 10.4 GeV compared to the W plus, which is around 81 GeV. And the question is, we understand this in the standard model by the mixing. The question is, maybe this is a similar dynamic mechanism as I just explained for the rho, and I will come back to this. In the case of the rho meson, we have a quark and antiquark inside. In case of the W boson, if it's composite, then the question is, what are the constituents inside? Well, first of all, these constituents, they would also be confined, but the confinement radius must be much smaller than the confinement radius for the quarks, which is given by the QCD scale lambda c, and it's around 10 to minus 14 centimeter. So there's a factor of at least, because the weak bosons should have not a scale larger than the size of the quarks and leptons, which I take to be of the order of 10 to minus 17 centimeter, close to the experimental limit. There must be at least a factor of 1,000 here between the weak bosons and the Rho mesons. And now the constituents of the weak bosons would be just new kinds of constituents, and I assume them to be left-handed fermions. Left-handed because of the left-handed nature of the weak interactions. I call them alpha and beta. The name of these constituents was suggested to me by Murray Gell-Mann, but he knew that the haplos in the Greek language means simple. So we call these constituents haplons. Salam calls them preons, for example, or subquarks, but I like the name haplons. And they are alpha and beta. The charges are not uniquely defined, but the charges must be such that you get the right charges for the weak bosons. And I assume that the sum of the alpha and beta charges is 0, and then it's fixed to be plus 1/2 and minus 1/2. Then you can make up the W plus, the W minus, and the W3. And these would be the wave functions of these particles. And the gauge theory which confines these particles, these constituents, to produce the weak bosons as bound states, I call QHD H for haplon. And unlike QCD, such a theory should, I think, should be a chiral gauge theory. And nothing much is known about chiral gauge theory, so for the time being. The QCD group at CERN is now just starting to do some investigation about this. But I assume it to be a chiral gauge theory. And the gauge bosons I call glutons, because glu in English means gluten in Latin. And so I combine Latin and Greek and call them glutons. You know, in QCD, the gauge bosons are gluons, a name I never liked. And I proposed a long time ago one should call them chromons, from chromos, from color. But Gell-Mann insisted we call them gluons, so the name got stuck. It's not a good name. But this name might be better. Let's call them glutons. And the gauge group of the QHD group, I don't know yet. Probably it's a unitary group. Let's assume it's SUN. N could be anything from n equal 2 to n equal 10 or whatever. It could also be SU3 like in QCD. Now in QCD we have these duality diagrams. A Rho meson decaying into two pions shows this behavior here. You create a quark and a quark pair here, and that's all. And in QHD you should have a similar duality diagram, where a weak boson, when it decays in the U and an anti-down quark, goes down here. Then the same constituents should also go inside the leptons and quarks. And that would imply that leptons and quarks are also composite. And this I will discuss at the end. For the time being, I will concentrate on the weak bosons. And the universality of the coupling constant, which is usually attributed in the standard model to the gauge invariance of the theory, to the fact that these are gauge bosons, follows here again in the same way for the Rho mesons, that was calculated by Gell-Mann and Sakurai a long time ago, the same mechanism. On the other hand, we know that parity is maximally violated in nature. And this is in the standard model described by the left-handed SU2 group times U1. But this would be very difficult to implement if the weak bosons are composite. So I assume that this is a subgroup of a group SU2 left times SU2 right times U1, which was also discussed a long time ago by Abdus Salam in detail. It's a left-right symmetric group, and the parity violation is coming simply because the masses of the gauge bosons for the right-handed SU2 are much heavier than the one for the left. So if you start out from that group, it's quite clear the masses of the W right. The present limit on this is around 600-700 GeV. I assume it will be larger than 1 TeV. Now in the standard model, then you embed the standard model into this group. And now you realize in the standard model the U1 gauge group is something very funny. It's different from left to right. It's a strange charge. It's given by the weak hypercharges, which are different for left-handed and right-handed particles. And now if you have this group instead, SU3 of color times SU2 times SU2 times U1, then the U1 group is much simpler. It's just the group for baryon number minus lepton number, vectorial. Much simpler. That was also figured out by Abdus Salam a long time ago. And so you could embed here. What you do is you embed this U1 group and the SU3 in the group SU4. And that is a group which takes simply the 3 colors of the quarks and the lepton as a 4th color. And then you have this group. And that was discussed by Paddy and Salam a long time ago. You have a structure like this. The 3 colored quarks, a neutrino and the lepton. And that's precisely the Paddy-Salam framework. Paddy and Salam, however, then had a complicated breaking of this group. In my case, I just take it to be the breaking such that you take QCD as an exact group and then the leptons are split off, while Paddy and Salam were breaking this group continuously. And then we arranged even integral charges for the quarks. Now this group, SU4 times SU2 times SU2, is a nice group. It doesn't have any U1 factor anymore. And as you will perhaps know, this group can also be easily embedded in a grand unified theory in the group SO10. But anyway, the left-handed group is given by these constituents. The right-handed group is also given by the same type of constituents, alpha and beta, but these would be right-handed particles. And the confinement scale for the right-handed particles here for SO2 right is much higher than the one for the left. So I make this smaller than this one. And then the gauge group for QHD is actually a chiral group, SUN left times SUN right. Well, it could also be another number here, but I assume the number to be the same to make it more symmetric. There's just the confinement scale which is different. So the confinement scale for the left-handed one is much less than for the right. And the parity violation is coming simply from the fact that the confinement scale for the left-handed group is much smaller than for the right. Now a rho meson, the size of a rho meson is given by the lambda C parameter, the QCD scale parameter. The size of the weak boson, which is a left-handed weak boson, is given by lambda sub L. And the question is then, how big is lambda sub L? Can we figure it out from the experiments? Well, there is a way. I compare this again to the QCD mechanism, the mixing of the rho with the photon. Rho, photon, and so on. And this mixing, as I explained before, is given by this mixing parameter M that gives a 3.1 MeV, which I had. And now I do the same thing for the weak boson. Now the neutral weak boson, or the Z boson if you like, can annihilate the megaphoton and, sorry, too fast. Can make a photon, come back to the weak boson, make a photon again, and so on. That leads to a mixing. And the mixing parameter, the formula is the same. Here, when I go back, here, this is this rho 0, rho plus squared, 1 minus m squared. We get the same formula for the weak bosons. Now, in the standard model, we have a similar equation. mz squared and mw squared over 1 minus sine squared theta w. The same equation as this one here, except m is now the sine of theta w. Here, the sine of the Weinberg angle is now the mixing parameter m. So we have these two equations which must be the same. So we fix m to be the sine of the Weinberg angle, which is measured very well, 0.485. And then I look at the mixing we see in nature, the Z boson and the W. I interpret it now by this dynamic mixing mechanism. I don't have a Higgs mechanism, I just take this mixing mechanism. And I get the same thing. In case of the rho, it's 3.1 MeV. So it is just a very small correction to the rho meson mass. In case of the weak boson, it's 10.4 GeV lifting up, which is much more, relatively speaking. But the reason is that the mixing barometer is much larger. In the case of the rho, it was 0.09. In case of the W, it's 0.45 or something. The weak decay, we can also look at the weak decay constant. It's given by this transition matrix element, just like for the rho meson, defines FW. And then the mixing barometer M is given by this equation. The same relation we had for the rho meson. Here we had F rho and M rho. Now I have M for FW divided by MW. And M is measured by the sine of the Weinberg angle. And you conclude FW is 125 GeV. Here I have the experimental numbers. For the fine structure constant, which defines E, I take the value measured with lab accelerator, which is larger than the normal alpha. And sine squared theta W is given here. So FW is very close to 125 GeV. Now, in case of F rho and lambda c is about the same. And so we could conclude that FW and lambda sub L should also be about the same. But of course, this is only an order of magnitude estimate because it depends on the gauge group of QHD, which we still don't know. So I take the lowest limit, the lowest value I take is 0.13 TeV, I mean 125 GeV, let's say, and maybe going up to 1 TeV or even larger. Depends on the details of the gauge group. Now the 0.13 TeV is very close to the experimental limit we have on this. I don't know precisely the value, but it must be around 0.14 TeV. Now if I take this value and I take this range for lambda sub L, I'm already quite specific for the band state theory of the weak bosons. But we still don't know what is the QHD gauge group. Now if SUN happens to be SU3 like in QCD, then there should be a similar equation. And then we are close to the experimental limit in that case. Then lambda L is around 0.13 TeV. But I take in general this range here. Now the right-handed lambda must be much larger than lambda L. I take it to be even larger than 1 TeV, but this may not be absolutely necessary. 1 TeV is about the limit. Now suppose such a theory is correct. What are how is it different from the standard model? First of all, you get new bosons. Because the Z boson, apart from the mixing, has this simple wave function. But there should also be an X boson, which is an isoscalar, which we have in QCD. It's the omega meson compared to the rho meson. And the X boson has this wave function. Now, people have looked for such particles. I predicted the possibility of such an X boson already around 1982, 83, and people were starting to look for it. And the present limit from LHC, I don't know the precise limit. It was they really didn't look for it much in detail, but I assume it to be of the order of 400 GeV. It's probably slightly less than that, but let's say 400 GeV. I will assume to be on the safe side that the mass of the X is 0.8 TeV, just for an example. So you have the Z, you have the X. Now the coupling of the X to lepton and quarks is similar to the one for the Z, because an X going to lepton and quarks by this diagram is the same as for the Z, apart from the plus or minus sign here in the wave function. That shouldn't count for this decay diagram. So the X decay can be related to the decay of the Z. And the Z decay is known from experiments. The width is 84 MeV. You can easily calculate if the mass of the X is 800 GeV, then the decay rate is 3.6 GeV, so it's quite large. You can also now add the other decay modes in the neutrinos, electron positron, into quarks. Quarks are 3 times larger than the leptons because of color. And so if you sum up everything, there are also decays of the X in W plus, W minus, and in the ZZ. If you sum up all these decay possibilities, I figure out the total width of the X should be around 200 GeV. It's a very broad resonance. I mean, the Z is only 2.5 GeV. And so the width of the X boson is very large and is comparable to the width of the rho meson compared to the mass of the rho. The mass of the rho is 750, the rho width is 150, and here the mass of the X is 200 GeV, and the mass is 800 GeV, so about in the same ratio. Now, how can you discover the X boson? Well, you have to look for the decay of the X in the two Z bosons. That's the most likely case. You can also look for mu plus, mu minus, and other things, but Z is very simple. So you would see in the LHC the events like this. Very clear picture. They have looked for it, so far they didn't find anything, but it's also quite clear because the energy is too small. They should find it when the energy is raised to 7 TeV in 2 years or 3 years from now. Number C is around 0.25, 0.3 GeV, and that implies the complexities of the strong interactions all at 1 GeV. Well, if lambda h is 0.3 TeV, which is a factor of 1,000 times the QCD parameter lambda, then you should see similar complexities, not of QCD, but of the QHD interaction. A factor of 1,000 times larger, around 1 TeV. And then now I come to the excited weak bosons. There would be excited weak bosons. I describe them by a weak isospin. The angular momentum J, SU2, I is the SU2 quantum number, and J is the angular momentum. Now, if I look at singlets of isospin, there should be a particle which I call S0, which is a scalar, then S1, which is a singlet, but it's a vector particle, and then also a tensor particle. For the triplet, you have a similar structure here, except it's now a triplet with always 3 particles like those. Now we have a similar feature in QCD. There is a scalar meson, usually called the sigma, which is extremely broad and has a mass between 5 and 700 MeV. The mass is very uncertain. Then there is a vector 1170 MeV and the tensor meson F2. These are all isospin singlets. And there is well, the question is, how can you understand why the sigma has such a small mass? The mass is even below the mass of the rho meson, which is an S wave, but this is a P wave meson. So the mass should be above 1 GeV. And normally we understand this because this particle can mix with the glue mesons. There are glue mesons, which were discussed yesterday in more detail, and there is a strong mixing with the sigma, and this could give a relatively low mass. In other words, the sigma is around 1.2 GeV, but then there is a mixing with the glue meson is pushed up, sigma is pushed down, until you get the sigma of 500 MeV. Now if I take this analogy, then in my case, the sigma would correspond to the S0, the H1 the S1, the F2 the S2. So I would have a mass spectrum which would look like this. I don't know the exact scale. I take it to be just above 0.1 TeV for an example, these three states. But then I would have, again in that theory also, a strong mixing with the gluton bosons, just like the sigma mixes with the glu mesons, and that would push the mass down. In other words, this mixing brings the mass down, and and I put it here to be just around 0.125 TeV or 125 GeV. Because I am going to identify this particle with the discovery at the LHC at 126 GeV. That would be the S0. So the S0 is now precisely these particles seen at the LHC, decaying into two photons, for example, into two Zs, two Ws, and so on. Now there would also be isospin triplets in QCD, which are well known. There is an isospin triplet, a scalar A0, a vector B1, and a tensor F2. And these particles would be analogous to my particles T0, T1, and T2, which are the triplet particles, angular momentum 0, 1, and 2. And so I would have a mass spectrum of these particles which looks like this. Here I plot the angular momentum. Sorry, that was too fast. And here's the W and the Z boson. Here the S0, S1, and S2. And the S0 I have already put in this mixing effect, so this fixes the scale. But once we know this scale from the experiment, the S1 and S2 are more or less, should be in this region here. Exactly, of course, I cannot calculate it. I can make an analogy with QCD, then come to precise numbers, but this is probably not very useful because the gauge group might be different than SU3, and also it's a chiral gauge theory, there are different features. And here are the three triplet bosons, T0, T1, and T2. Again, I don't know the precise masses, but the triplet bosons are certainly higher, because also they cannot mix with the gluton bosons. Now let's look at the S0 decays. The S0 can decay into W plus W minus or into ZZ. One of the particles must be always virtual because of the mass of the S0, which is less than twice the mass of the W boson. Now, but let's look at this decay. The S0 would decay with equal strength to W plus W minus, or the opposite, or W3, W3. But the W3 is a superposition of cosine theta W times the Z boson and the sine theta W times the photon. And when you put in these numbers, these are the numbers given by the Weinberg angle, then you immediately calculate that the S0 would decay into W plus W minus with a certain rate, which I call 100% just for comparison, into ZZ with 59%, so about 60% less. It would also decay into Z gamma is 36%, and into gamma gamma with 5%. So we have the case like this: W plus W minus, ZZ, Z gamma, or 2 gammas, 5%. Now the experiments give for this rate here 0.04. And that is the error I got recently from CERN. I'm not completely sure whether it's completely correct. And I expect from this simple calculation S0 decays into photons with a rate of 0.05. The Higgs boson, standard model Higgs boson, decays with a rate of about 0.015, which is already a certain problem with the interpretation of this. This is a bit larger than the expectation from the Higgs boson. Now let's look at the decay of the S1. The S1 can also decay like the S0 in the W plus W minus or ZZ, but it could also easily decay into 3 Z bosons or 1 Z and 2 gammas and so on. So it would not decay, however, because it's a vector particle. It would not decay into 2 gammas because of the Landau-Yang theorem. And so you could see decays like this. Very simple signatures for the LHC. Of course, so far nothing has been observed. Now, in nature we see 3 lepton quark families, which are given here, which you know. And the fundamental parameters are enormous. We have 24 fundamental fermions. We have 12 mass parameters. We have 10 mixing parameters for the leptons and quarks, 4 for the quarks and 6 for the leptons, including phase parameters for the Majorana neutrinos. The total number of parameters in the standard model is at least 28 parameters. So I would think the best way to calculate these parameters in the future is to have a theory in which leptons and quarks are composite. Now I already showed this diagram. A quark-antiquark pair, a W boson going into U in anti-D quark, here I forgot the bar. So you see that the haplons inside the weak bosons should also be inside leptons and quarks. And the simplest model, and I couldn't find any other model which is able to describe, roughly speaking, the standard model, is one in which leptons and quarks consist of these spin 1/2 haplons alpha and beta, and something else carrying color and lepton number. Now what is this something else? Well, I take it to be the simplest theory in which it's just a fermion and a scalar. In other words, a lepton and quark would look like this, a spin 1/2 haplon and a scalar particle. And then the lepton quark family is given by the weak isospin group SU2 here. That would be the structure. And here I take it to be the group SU4, which includes color, the U1 for the baryon number minus lepton number, and SU3 of color. And then I make up this group from the 2 fermions alpha and beta, generating the group SU2, and 4 scalars which are needed, 3 for the colors of the quarks. So there is a red, a green, and a blue scalar, and there is a black scalar making up the leptons. Leptons are black here, quarks are colored. And the charges of these scalars are fixed by the same mechanism as when I fix the alpha and beta charges to be plus and minus 1/2, as I said before. These charges must be plus 1/6 for the red, green, and blue. And that immediately describes charge quantization. The basic interaction in that theory are similar to QCD, or to the standard model, except now I have also here these gluton bosons interacting with the spin 1/2 haplons and with the spin 0 haplons. And of course the photon makes interactions with the spin 1/2 haplons and the spin 0 haplons. The leptons then would look like this, a spin 1/2 haplon and a spin 0. A red quark has a spin 1/2 haplon and a red scalar. An electron, suppose you look at a moving electron, then the electron would consist of a spin 1/2 haplon going along this black arrow here, accompanied with these black squares, which is a spin 1/2 haplon. And a red quark would have again, sorry, too fast, it would be the spin 1/2 haplon, which is black, and then the red scalar going with it. Well, suppose this 126 GeV particles in at the LHC would be the Higgs boson. Then you can easily calculate the decay rate in the electrons, muons, and tauons are such that only the tau is the leading candidate. It goes with the square of the masses. The electrons and the muons you can forget. If the S0 is a bound state, it can also decay into leptons, for example in the tau leptons. But I cannot, unlike in the standard model, I cannot really calculate this basic decay rate. I can estimate it roughly, but I don't get any very precise number for this decay rate. But then you would see these decays as seem to be seen as the LHC. But I would not expect a strong decay of the S0 into mu plus mu minus, because the muons is much lighter than the tau, and then there should be rather decays like in the 4 muons, or in the 2 electrons and 2 muons. It's just like we have for the raw mesons. The excited mesons don't like to decay into pi plus pi minus, they decay into 4 pions or sometimes into 6 pions. So you would have decay patterns like this. But if you sum up the energies of the 4 muons, you would get the mass of the S0. Now, another thing I want to mention at the end are again, is related to the one-state structure of the leptons and quarks. The leptons and quarks here, this is spin 1/2 haplon, the spin 0 haplon, bound together strongly by the QHD force, and they would be like the quarks in a raw meson, they would be in an S wave. But you could also excite the leptons and quarks to make a P wave. That would be the angular momentum equal to 1. So we would have angular momentum to 1 and spin 1/2, and then you get new states which have spin 3/2 or spin 1/2. In other words, you have, for example, the up quark has now there's an excited up quark, or double excited up quark, well, whatever you like it to call it. That has J equal 1/2, that's J equals 3/2. The masses of these objects depend on the details of the QHD dynamics, and I can only roughly estimate it, but I would think it's at least 1 TeV. Maybe slightly less than 1 TeV, but not much less. Now, how would it decay? The U star could easily decay into an up quark and a photon, or an up quark and a Z boson. So suppose at the LHC, when we reach the energy of 7 TeV, then you look at the collision of 2 quarks. 2 quarks collide, and then what can happen is that out comes a normal quark, but the other quark is excited. It's a Q star. And so at the end, when you look at what you should see at the LHC, is a gamma ray coming out with very large energy at least 500 GeV, and with the other side, something with a similar energy, but these are just given by the fragmentation of the quark. Here's a quark emitted with high energy, producing a jet of quarks. A jet of pions, a jet of particles, mostly pions. If you sum up the energy here and the sum of the energy here, then you should be able to calculate the invariant mass of the excited quark. And now I come to the conclusions. I said the weak bosons, the leptons and quarks are composite objects. Then the S0, I interpret to be just as an excited weak boson with a mass of 126 GeV, and that fixes the masses of the other excited weak bosons quite well. They have not been seen yet, but if I'm correct, they should. The next excited weak boson, let's say the S1, should be seen within the next 1 or 2 years. So that is the S0. And that's my last slide now. If I'm correct, then with the LHC we should see once you are the next energy region of 7 TeV against 7 TeV, we should observe an enormous number of new particles, just as many as we see in QCD, above 1 GeV. We see now here at the energy above 1 TeV, hundreds of new particles. It will be very difficult to figure out details, but certainly this is much different than what you would expect with a standard model, where you would see nothing except the Higgs boson coming out, and then that would be the end of particle physics, and that would be the start of a new particle physics. So thanks, that's all, thank you.
Thank you very much, and questions? comments?
Here's one.
So the sigma meson has a very broad resonance, and so would you expect then in analogy for this S0 to also have a broad resonance?
No. It's broad. It depends on the decay. The sigma is very broad because it coupled very strongly to the pions. The coupling of the S0 to the leptons and quarks and to the weak bosons is just less than that. So I cannot predict how broad that resonance is. That's very difficult to say.
Yeah.
You made the analogy between rho mesons and weak bosons.
Yeah.
So rho naught went up, but rho naught is a broad resonance. On the other hand, Z naught is a very narrow resonance. In fact, you took the broad resonance as the X, but Z being a narrow resonance and rho naught being a broad resonance seem to be in some kind of a conflict with the basic
No, I don't think
you had.
I don't think it's a conflict. It has to do with the details of the coupling. The rho couples very strongly to pions, the 3 pions, 2 pions, and they decay quickly. And the Z boson just has a smaller couplings. The coupling constant of these weak bosons to the leptons and quarks are given by the dynamics of QHD, of that new confining theory. And it's a chiral gauge theory is different from QCD. And so details I really cannot, I can only estimate it, but I cannot really calculate it. That would have to be done in the future. So it's, I think it's not it's a bit worrisome, but I don't worry too much about this aspect now.
On the other hand, since the X boson, that one around 800 MeV, you expected it to be very broad resonance.
Yeah.
If it is so broad, how do you identify it? Would it just go off in the continuum? I mean, even if one extends...
No, but it's just
feature.
like people found out the rho meson. The rho meson has a width of 150 MeV, and they could see it. And we would see it here also. You would see, for example, it decaying in the 2 Zs, or in the 2 gammas. No, let's say 2 Zs. And then you see these events. If you sum up, you get a bright Wigner shape, and then but you need lots of data for this. It will take many years. I don't think the discovery of the X boson is such a thing which can happen very quickly. It would be much easier to see the S1, for example. The S1 could be seen even the next month. Once any of these particles is seen, of course, then it would mean the end of the standard model, the end of the Higgs mechanism.
What
And
about,
I just wait for this.
what about the photon? Is it also a composite
No,
boson in
no,
your philosophy?
no. All the gauge bosons in that theory are massless. These are the photons, the gluons, and the glutons, and they're completely massless. And anything which has a masses are generated by a confinement mechanism. It's a nice, then you understand why mass is such a universal quantity. I don't like the standard model where the mass of the nucleon is given nicely by QCD, and the mass of the weak boson is something completely different, coming from the spontaneous symmetry breaking. I don't like this asymmetry.
So all fermions are composite, is it?
Yeah.
I mean, you don't have something like a lepton.
Hmm?
You don't have something like a lepton.
Yeah, leptons are also composite.
Lepton is also composite.
Yeah.
So there is nothing like a present leptons. See, today we use E and mu for seeing lots of things because E and mu are elementary particles. So we don't have anything like a asymptotically free fermion available for probe.
No, just leptons or quarks are composite. That's okay. There's no problem with that. And we would see this compositeness easily in the future accelerators. If leptons or quarks are really composite on the scale I was saying, it would be very nice to have also the linear collider. Then you would see it directly.
One more compact than the other.
Yeah. And in principle, in such a theory, this is far remote, but in principle you are able also to calculate the lepton and quark masses. Everything could be calculated at the end, just from self-energy effects. At present I'm doing this actually with somebody at the Max Planck Institute in Munich. It's very difficult and depends on many things, but I'm trying to work on it. And I always, in my theory, I can also not understand that feature of the standard model, which is very intriguing, very strange, that we have three colors of the quarks, we have three generations of leptons and quarks, and we have three dimensions of space, always at number 3. This is again an accident here. So eventually, we should find a theory where this is coming out naturally, but I don't know when it happens.
What about the precision tests? The precision tests of the electroweak part of the standard model,
that is okay.
You will be able to reproduce with your composite picture, you think?
Yeah, but not at the present time. At the present time, the precision tests are not good enough. And the best thing is the muon, the anomalous magnetic moment of the muon, where there are some discrepancies with the standard model, which I don't take seriously, however. And that kind of precision test could eventually give a limit. But as I said, the size of leptons and quarks in that theory is probably a factor of 10 below the present limit, which is 10 to minus 17 centimeter.
So you will continue to use the standard model as an effective theory and calculate?
Oh yeah, the standard model is an effective theory, just like the Romeson theory of Sakurai is an effective theory, not a basic gauge theory. It would be the same thing.
So can I just continue with what you just said? I would just like to understand that better. Usually the constraint from precision electroweak tests on these extra resonances are quite strong. They would constrain to be bigger than 1 or 2 TeV. So I'm kind of puzzled why you say that they're not constraining this theory very strongly.
No, I don't understand these tests too well, but in this theory, in this precision test, one assumes, let's say, limits on the Z prime. One assumes that the Z prime decays in the same way as the Z, the same decay pattern. That's not the case here. An excited weak boson would decay hardly in the leptons, would mostly decay in the weak bosons. And things are complete, and also in the many leptons, 4 leptons instead of 2 leptons.
No, I'm not asking about direct constraints, but just in the 2-point functions of the W and the Z, you can have these particles contributing, which would affect S and T.
Now, this I haven't studied, but I think there is no problem. And it depends. You might get a result for the confinement radius of the theory. But I can always put this confinement radius just above the present limit.
Which would be very strong. It would be above a TeV.
No, I don't think so.
Okay.
I don't think.
The constraint will appear only on the couplings of the Z, that kind of couplings. The couplings constraint coupling, that's all. So you can always only the coupling. Yeah, of course. But
yeah, the coupling can be small. It's not usually in these precision tests. The excited weak boson W prime, Z prime, and assumes that the coupling to the lepton pair is the same as the Z, and that's certainly not the case here.
So I just wonder what's the how can we actually distinguish fundamental elementary particle and composite particle? As far as I know, if it is fundamental elementary particle, there is no excited state. But if you have a bound state, it must be some excited state. So can we expect some excited state of electron and muon and other?
Yeah, I mentioned these at the end. There are excited quarks. There are quarks with spin 3½ spin 5½ 7½ and so on. Yeah, excited quarks.
So we
excited neutrinos. There would be neutrinos which have spin 3½ and have a mass of 1.5 or 2 TeV. Very funny objects.
So we can expect in the high energy, we can expect more excited.
Oh yeah. But it happens only above 1 TeV. Oh. Just like in QCD where things happen above 1 TeV. Just a factor of 1,000. Roughly a factor of 1,000.